Welcome, folks. So building off of one of our earlier pre-works where we looked at properties of exponents, we're now going to look at properties of nth roots. We're going to redefine nth roots and then work some examples. So what is an nth root? Well, an nth root is simply a number that when we raise to the nth power, we get a particular value, and so we would say that the prior value that we raised is an nth root of that number. That can seem a little bit confusing, so let's go ahead and clarify it. We know for a fact that 2 when raised to the fifth power is equal to 32. So we would say that 2 is a fifth root of 32. Likewise, if we took the number 3 and squared it, we'd get 9. If we took the number -3 and squared it, we'd get 9. So we say that both 3 and -3 are square roots of 9. Notice that this is plural. There are 2 square roots of the number 9 here. Continuing, if we were to take the number -2, or 1 plus the square root of 3i, or 1 minus the square root of 3i, we would find that these are all 3 cube roots of the number -8. Now, you might be a little rusty with working with complex numbers. No worries, we're going to do a review of those. But you should be able to verify that if you took the number -2 and cubed it, that you'd have -2 times -2 times -2. That's just what we mean by exponents. We explored that last time. And that would be, the first product gives us 4 times -2, and that indeed gives us -8. And so because -2, when raised to the third power, gives us -8, we say that -2 is a cube root of -8. Now, you might be surprised to see this, or maybe you knew this, but you could verify that if you took 1 plus the square root of 3i and cubed that number, or 1 minus the square root of 3i and cubed that number, you would indeed also get -8. Yeah? So don't worry about that if you're not sure where those come from. We're going to explore that over the rest of the semester. But one of the goals of this course is to look at this equation right here, x to the n equals b. And we will discuss how this equation has n distinct solutions. So for example, in b above, we showed that there were 2 square roots of the number 9, corresponding to the 2 solutions to this equation right here, x squared equals 9. If we try to find the numbers that make x squared equals 9 true, we found 2 of them, 3 and -3. And so those are the 2 square roots. So notice what I'm trying to emphasize is we had 2 solutions to this equation, and those are precisely the 2 square roots to 9. In C above, we showed that there were 3 cube roots to the number -8. If we go back, look up here at C, we found 1, 2, 3 cube roots of -8. And that's precisely the 3 solutions, the 3 values that we could plug into this equation to make it true. So while we didn't list them all out, there are actually 5 fifth roots of 32, corresponding to the 5 solutions to this equation right here. What would this equation be? It would be x to the fifth equals 32. So certainly you could check that if you took 2 and raised it to the fifth power, that's true, but there are actually 4 other distinct solutions that we want to learn to go find. And that can be decently challenging. We're going to eventually use trigonometry to help us do that. So one of the goals of this course is building towards finding solutions of x to the n equals b. And we expect, if we're talking about, say, x to the 6th power, we would expect to find 6 solutions, 6 roots to that equation. So continuing along, one of the things that can be very confusing about this is that we often have multiple roots. So for example, we had 2 square roots, we had 3 cube roots, and so what we want to do is sometimes distinguish between just finding a particular root to a number, and that's where we're going to introduce this idea of the principal nth root of a real number. And so when thinking of evaluating an nth root, we want the nth root operation to only return one value. So I want to begin thinking about the function, say f of x equals the square root of x. What's the problem? Well, there are 2 square roots of 9. There were 3 and -3. But when I want to evaluate, and this is the operation that you usually see for finding the principal root, when we want to evaluate the square root of 9, I only want this to return one value. Okay? So if we do so, then the expression f of x equals square root of x would be a function. That is, when you go to plug 9 into the function, you would take the square root of 9 and you would get only one answer. We only want one principal root to that for this to be a function. And if we do so, then we see that the domain value 9 is paired with exactly one range value, 3. That is, the only ordered pair that we have for this would be the ordered pair 9, 3. We don't want to also have the ordered pair 9, negative 3, and if we did, you would see right away that this relation through the something called the vertical line test, that this relation wouldn't be a function. So we only want this one solution. So here's our technical definition that kind of it's a little bit wordy, but it sort of gets us around that issue here. So suppose n is an even positive integer. So I'm talking about even roots here. This could be square roots, fourth roots, sixth roots. Okay? Then for a and b both real positive numbers, if a to the n equals b, then we're going to say that the principal nth root of the real number a is b, and we'll just write it this way. So now we're introducing this nth root notation here. Similarly, we'll do the same thing when n is an odd integer, but we don't have to be quite as careful. All I have to specify is that a and b are real numbers, and then if that's the case, then we would call that the principal nth root. So there's only one here. So all of this is sort of lengthy math verbiage to get around the fact that sometimes I don't want all of the roots to a particular equation. I just want something called the principal root. So I'm going to say, don't worry about this. I was pretty careful with my wording of it. Don't worry about this too much, but instead, this is the takeaway. Okay. Even though there were two square roots of the number 9, when you see this operation here, compute the square root of 9, there's only one answer to that, and the only answer to that is 3. And we're not going to use negative 3, even though it is a square root of 9. Why? If you look at the wording up here, it said, hey, because you have 3 squared is equal to 9, and both 3 and 9 are positive numbers, that's what this is saying right here, and we're talking about an even root, then the only principal root is the number 3. There is no other even number that when we, or excuse me, there is no other positive number that when we square it, we get 9. Okay. A little bit different here, we're looking for the cube root of negative 8, so n here is odd. And here it doesn't matter. As long as we find a real number that makes that true, that will be the principal root. So again, if you go back and look at our roots to the number negative 8, we had 3 cube roots, negative 2 and these 2 imaginary ones, but we only want the real one when we're evaluating this expression right here. So here I'm using the principal cube root, and that needs to be a real number, and so that would be the only real number that makes that true in this case would be negative 2, and that would be the only solution we give to it, even though there are 2 other cube roots to the number 8. So that's all a little bit complicated, and maybe you've not, maybe you've just kind of worked with these before and never wondered about this, but I want to distinguish between evaluating these roots and solving the equations that we were just looking at, solving these equations that look like x to the n equals b. Okay? So in this class, and generally I think this is a good rule of thumb, that when you see this expression, the nth root of b, I only want you to give the principal nth real root. Okay? And that applies whenever the conditions of these two statements are met. So let's go ahead and let's hopefully clarify that a little bit. So I want you to compare and contrast these two statements here. Here we're being asked to solve x to the n equals b, versus over here we're being asked to evaluate the nth root of b. Okay. So here, first of all, the first thing we should say is there should be n solutions. So there are n solutions to this equation. In this, we're doing a mathematical operation, and so if we want to think of that as a function, there is only going to be one solution, only one value that this evaluates to. Okay? And one thing I want to add about this equation, when we're solving x to the n equals b, these other solutions, there's n of them, but they're often complex solutions. So it depends whether or not we give all n solutions or not, depends on whether we're going to consider the complex solutions. So for example, if we were to solve x cubed equals 8 in the x cubed equals negative 8 in the complex numbers, we would get three solutions. X is equal to negative 2, x is equal to 1 plus the square root of 3i, and x is equal to 1 minus the square root of 3i. Versus if I asked you to solve x cubed equals negative 8 in the reals, then we only have one solution, and here we can use something called the cube root operation. Because it's a well-defined operation, we can take the cube root of both sides of the expression. So let me do so. We would take the cube root of both sides here. And in doing so, we would end up with x is equal to negative 2, and we get the only one solution if we were solving this in the real numbers. So this equation itself has its own complexities, whether or not we're going to consider complex roots or not, and the tools we have available for us. Okay? But I want you to be careful here, because if I said solve x squared equals 9, there are always two solutions to this. We would have x squared minus 9 equals 0, and we could factor this to be x plus 3 times x minus 3 equals 0. And then by the zero product property, we get two solutions, x equals negative 3 and x equals 3. So those are the two solutions to this equation here. And those are both real solutions, so we do need both those solutions. So this has to do with solving the equation x squared equals 9. Over here, though, if I asked you for the square root of 9, we've just said that there is only one solution to this. And we're only looking for, it's not even really a solution, there's only one value to the square root of 9. So hopefully that gives you a little bit of clarification, folks. When do you need to be more careful? When are you looking for multiple values? And it has to do with when you're solving an equation that involves finding nth roots versus simply evaluating the principal root. So again, this is called this is finding the principal nth root of a real number. Okay. So let's go ahead and see if we can clarify that a little bit, and then we'll take a break. So here we're asked to solve the equation x squared equals 25. So some of you may know that there are two answers to this, x equals 5 and x equals negative 5, and you're able to get there right away. But I want to warn you, because I see people make mistakes with square roots all the time. Let's go ahead and do this work in its entirety. So the first thing I do is I subtract the 25 over, and then I can go ahead and factor the polynomial that's on the right. So I've got x plus 5 and x minus 5 is equal to 0. Then I can set each of those two factors equal to 0 by the zero product property. And that gives me the solutions x equals negative 5 or x equals 5, which are the two solutions to this. So I'd like you to do the same. Again, you may know that the answers to this are 7 and minus 7, but I want you to get there using this work. So then in the next problem, we're asked to evaluate the square root of 25. When we're asked to evaluate the square root of 25, because 25 is a positive number and this is an even root, we expect there to be only one solution, and that is the positive number 5. In this case, we want only the principal root to this, and we don't want negative 5. That's not what we return when we use the square root symbol. Here it's a little bit easier. When you're dealing with your odd roots, if you find a real number that solves it, you're done. That's it. And in fact, if we were to ask the question, what number when we cube it gives us negative 27, there's only one real number, and that is that the cube root of negative 27 is equal to negative 3. Okay? So to clarify, and in this class, we are going to switch up partway through the class, but right now we're just saying in the real number system, I'm asking you to find the fourth root of negative 81. There is no number, there is no real number that when I multiply it to the by itself 4 times, that I get the number negative 81. So this has no real solution. Okay? Or the result is non-real. So be careful here. It is possible to take the nth roots of odd numbers. It's possible to find a principal root. To take the nth root of a negative number if n is odd. So here we've got a cube root, and we can find the cube root of a negative number. Here I'm asking you for the fourth root of a negative number, and in the real number system, we cannot do that. We will learn how to find them in the complex numbers later on in this course. Okay, so I'll see you in the next video. But what I'd like you to do in the meantime is work these 1, 2, 3, 4 problems. I'm not going to give you solutions to these. They're virtually identical to the ones that I've done. So I'll let you just do those on your own, and I'll see you in the next video.